Stereochemical issue of SN2 reaction today. So again, your electrophile, which is buried in the leading group, has 4 different constituents. And you substitute that leading group for the nucleophile, you're going to get conversion to the stereogenic center. So we'll look at a couple problems with that. We'll look at the sequence of taking thymidine to ADP. How there was that issue of having 2 alcohols in a molecule, how do we deal with that, get the azide in. And that will wrap up SN2, and pending time we have left over, we'll introduce SN1. So again, the rate of the reaction, SN2 versus SN1, is dependent on the class of the leading group. So far we've said tertiaries do not react by SN2, but they do react by SN1, and that necessitates a change in the reaction condition. So the nature of the electrophile versus the nature of the nucleophile and the solvent that's used. So as we start learning more of these reactions, it's going to be really important that you're able to spot what the conditions are telling you relative to the functional group, so you know how the mechanism proceeds and what products you end up with. Any questions? One other thing, so there's been about 17 students that signed up to do the bonus video. 2 people have submitted theirs, 2 or 3 more have filmed theirs. So keep in mind, if you want to do that, it's worth 20 points. And I'll send out announcements when you can get the kit, but ultimately you have to have that video submitted in Canvas by December 5th. And that's now less than a month away. Keep in mind, I'm busy with other things, so when I send out those announcements, if you do have the time, just come and get it over with so you at least have the video recorded. So we'll continue on with some questions about SN2, and then we'll get into the stereochemistry. Again, in preface for the final, you'll see some questions that ask you to rank substrates, and that's what this question is based on. So we have 3 substrates that are all bromine, so that's the common factor. So something else differentiates them. In the reaction with sodium methoxide, so that's a strong nucleophile. Again, it's ionic, Na plus, OMe minus. And the solvent is polar, aprotic. So it's asking what is the rate from fastest to slowest. So again, keep in mind the nature of, the greater than or less than signs in the responses as you're, interpreting them. So the first thing I would do is just classify the carbon-bromine bond for each, reorder them so that they're ranked according to what this is asking. The first one is a tertiary alkyl bromide. The second one is primary, but then it's also allylic. So again, that makes a difference. And then the third one is secondary. So the SN2 rate trend was methyl greater than primary, greater than secondary, and essentially tertiaries won't react. So when we look at, converting that number 1, 2, or 3, we're just going to stick it in that order. So substrate number 2 will react the fastest, so greater than 3. And then substrate 1 essentially won't react, so it's going to be last. So then we find what response matches that, and that would be B. Yeah.
Will it be faster than if it was not diluted?
Yeah, so again, the nuance to that question really lies right here in the secondary. So when you get into a comparison of like primary allylic versus secondary allylic or something like that, generally primary reacts first, but allylic's going to trump everything for the most part. And again, the secondary is the one that's probably going to give you the most issue in determining does it do SN2 or SN1. So as we'll see today when we shine a little bit more light on the complicating factors, you really have to pay attention to the solvent and the nucleophile that are present. And again, the secondary is highlighted there because as you get older in life, your decisions, well, it depends. So everything depends on the context. But tertiaries are pretty much SN1. Primary and methyl are SN2, and then secondary is the gray area. So here's another common type of problem that you'll see. In lab, we just say starting material and product, so S, M, or P, and then what reagent would carry out that transformation. So when you look at it, what's changing is the iodide is substituted for azide. So we have a secondary for both. And so really it's a substitution at that carbon, and we need to figure out what reagent is going to supply N3 to that. So immediately for choice A, you can see that there's no elements of N3. So that's out. C also has no N3 in it. And then you're left with B and D. So the main difference between them, they both have N3. But if you convert that one into the Lewis dot, you'll see that there's a bond between iodine in one of the nitrogens. Whereas with D, you have Na plus N3 minus, so that's ionic. So that would be the preferred reagent for an SN2 reaction. You have a strong nucleophile, the lone pair on nitrogen is exposed, it can do the displacement. So in terms of the nucleophile strength, ionic is always greater than the neutral compound. And on Wednesday, we finished up with showing that carbon anions, so carbanions can be nucleophiles as well. And one of them is based off alkynes. And so this question is asking you to make 2-hexyne. So we know that the Y is telling us there's a triple bond, and the 2 is telling us the start position of that triple bond. So there's 3 carbons, 1, 2, 3, the start of the triple bond, and then we have 3 more. So we want to make that using one of those choices, A, B, C, or D. And another tip for the final exam is normally how the ACS exams are written, there's 2 distractor answers, like answers that just make no sense. Then the 2 that are left are the ones that are really testing your ability to answer that question. So for this type of question, numbering the chain really helps, because then when you look at some of these responses, they're either going to have more carbons than you need or less carbons. And then you could say, okay, that's not going to get me the correct answer. So in terms of the mechanism, it's going to be SN2. So when we look at the way this is written, the left reagent is the electrophile, and then the right side reagent is the nucleophile. So maybe using that first tip, in terms of the number of carbon atoms, can you eliminate one choice immediately? I guess 2 choices. So I heard some C's. So if we start numbering, so the methyl group is sort of our start point. There is 1. So 1, 2, 3. This would have to be carbon 4, 5, 6, 7. So that's too many. Choice B, 1, 2, 3, 4, 5. That's not enough. Choice D is really crappy as well, because notice everything's neutral. So you don't have a carbon anion there. And then here, there's no leaving group. So just with that, A is going to be the correct answer. And so it's an SN2 reaction because the nucleophile attacks the carbon bearing the leaving group. That leaves, and we end up with the alkyne we want, and then the inorganic byproduct, sodium bromide. Any questions on that? So maybe let me just point out now, so in that product, that was the bond that we made. But then we could also make that molecule using the other side. So I'll dissect that one in green. You could also make that bond, and then the left-hand side would be your electrophile, the right-hand side would be your nucleophile. So you could put the negative charge at carbon 2, and then use methyl iodide as the electrophile. So now this last sort of part for SN2 is probably the most complicated in the sense of, now models will really help you, but the visualization is what is key to understanding this. If we look at carbons bearing the leaving group, but they're also stereogenic centers, what's going to happen is when the nucleophile displaces it, there'll be an inversion of that stereo center. So we represent that with the wedge or the dash, and then we also have to figure out the R and the S nomenclature. So I want to say for 95% of the time, if you start with R and then you displace with the nucleophile, the product will have S. But you still have to validate that using the rules, because sometimes the priorities will not change to give you that R to S or S to R flip. So if we look at the reaction shown, 2-bromobutane, that's a secondary bromide. And so that has that H going back. So there's 4 substituents. That's a stereo center. We have bromine, we have H, we have methyl, and then ethyl on the other side. Because the nucleophile has to attack the carbon leaving group at 180 degrees due to the antibonding orbital, the stereo center inverts. So Na plus, N3 minus. It's going to attack from the opposite side of that bromine. And so that H then sort of comes forward. And then the nucleophile is now on the opposite face. And so the SN2 mechanism occurs with inversion of the stereo center. So we'll look at why that is, and we'll look at some questions. We know that, just by looking at the starting material and product, that carbon bearing the bromine or the azide is sp3 hybridized. So how does the inversion happen? So at the transition state where you're making a carbon-nitrogen bond and breaking carbon-bromine, the carbon becomes sp2 hybridized. So at that point, we know that sp2 hybridization is trigonal planar. So the methyl, the proton, and the ethyl group are all in the same plane. And then as the reaction proceeds, they then invert. So a drawing of that, I can sort of rotate and flip in my mind. So I think I'll show the I want to write these things correct. So I'm trying to think what goes where. goes where? In the wedge? Okay. CH3, and then what do you think? I'll put that burden on you. I'm feeling a little sick, so my mental processes are slower than normal. What do you think goes up? So we'll put the H up. And then down here is the ethyl group. So those three substituents, the H, the methyl, and the ethyl, because that carbon's sp2, they now all lie in the same plane. And so as you form that carbon-nitrogen bond, they're all going to sort of flip backwards to the other side, and then the bromine's going to leave. So ultimately, those three groups go from sort of one side, planar in the transition state, and then flip or invert to the other side. Anyone watch Andy Math on YouTube? You know who that is? So he solves math problems in like 4 minutes. It's a really nice channel if you want to review things, but he says we'll put a box around it. So we put some brackets around it. That's the transition state. Again, that's the highest point in the energy diagram. Once you get there, then the reaction proceeds pretty fast. So now the issue is we cannot assume that just because it's inverting R goes to S, you still have to do the SIP, apply the SIP rules to figure out if it really did. So in this problem, we'll go through that exercise of assigning R and S using atomic number as the priority. So we put our hydrogens in there to facilitate that. And I'll change the color here to blue. Or maybe I don't have purple, but so bromine's going to be 1. Hydrogen will be 4. Now you have the 2 carbon groups. Since they're both equal, you go out to the next atom. The ethyl group will then take priority. So that's 2 and that's 3. So it looks like we're going clockwise. So the bromide should be R. So that gets rid of A and C. And then I'll do the azide in green. So hydrogen gets 4. Nitrogen's going to take priority 1. And then the same thing, the ethyl group gets 2 and 3. So you're going clockwise, but since that H is towards you, we have to flip it so that becomes S. And then we would end up with D as the correct answer. So we do see the R to S inversion, but again, you can't always assume that's going to happen. So this question is another SN2 practice, and my advice is to draw the product out, then go through the same exercise. So this one's probably probably easier to see in terms of the inversion after we draw the product. So Na plus, OH minus. So that has to attack opposite to the leaving group. So we would draw OH carbon we're going to leave the hydrogen in the plane. So now it's going to be kind of over to the right. The methyl group is still coming out towards you. And then the rest of the chain, 6 carbons. Is going back. So this is probably the easiest way to interpret SN2 because you have, those 3 substituents on one side, and then in the product they're on the other side. So that's the inversion. And let's assign priorities here. Oxygen 1, hydrogen 4. The longer carbon chain will get 2, and then 3. Now what's complicating about this, because the hydrogen's in the plane, you really need your eyeball right here to interpret the 1, the 2, and the 3, if they're going clockwise or counterclockwise. If you do that, what do you think? Is it R or S? So 1 to 2 to 3. Again, if your eyeball is there, it looks like it's going counterclockwise, so that would be S. So that would be S2-octanol, which is choice A. So to check in, again, R and S you determine just through that algorithm of assigning priority. And the question asks, the measured specific rotation, again from polarimetry, plus or minus, is dependent upon the R or S designation. Let a screen out? Is it out? Okay, it's back on. Magic, magic. So that's false. Again, the plus minus is measured by polarimetry. So whatever it is, and then R and S determine from priority based on atomic number. So in terms of the kinetics, the solvent, and the nucleophile strength, what is required for SN2? So the 2 tells us that the kinetics are bimolecular, so we could eliminate B at this point. The solvent has to be polar and aprotic, so we can eliminate A and D, and then the nucleophile has to be strong, and what that means, you're typically looking for the ionic form. So M plus nucleophile minus. So C is the best response here. Yep.
For the nucleophile, you mentioned the other day that the pKa of the nucleophile has to be below 0, and does that apply specifically to SN2, or does that also apply to SN1?
So with the SN1, the nucleophiles are typically going to be neutral. So there you can get away with pKa's greater than 0. So in the reaction coordinate, it says the free energy of activation is positive, but overall the free energy change is negative. What term would best describe that process? So this is B. Again, with free energy, we're using the terms exergonic and endergonic. Enthalpy uses exothermic and exothermic. Anyone know what A and D relate to? They're actual words. So those are the derailer answers. They deal with how light shifts relative to someone observing it. So to summarize everything about SN2, you'll notice in the table here, the SN1 isn't filled out yet. The table will get filled out after we learn all that stuff, but this is a table that's nice to see or diagnose the reaction conditions to choose is it SN2 or SN1. So the electrophile rate, the nature of the leaving group, the nucleophile must be strong. So that means it should be an anionic nucleophile. Solvent, you want polar aprotic. The common examples of that are shown. Again, for organic chemistry, there's a lot of abbreviations used, so you'll have to know what DMSO means in terms of the name and then the structure. The 2 is for the kinetics, so it's second order. The rate equation involves the concentration of both the nucleophile and the electrophile. Stereochemistry, the center is inverted. And the last row says rearrangements. So in SN2, that's not a factor, but for SN1 it is. So again, that relates to the differences in those two mechanisms. Any questions on that summary? So to, again, put that into context, over the next probably 10 minutes or so, we'll look at the AZT synthesis, and then we'll finish up today's lecture on SN1. So now that we know a little bit more about substitution, as we return back to AZT, we identified that OH group is being substituted for azide. So everything we've seen today, look at the location of that azide. It's in the same sort of position as the OH. But we know that SN2 occurs with inversion. So essentially what has happened is that center has been inverted twice. So ultimately you get retention of the configuration. So right off the bat, that tells us something in terms of the reaction sequence that we have to consider. The other important thing to note is we said there's a primary alcohol and a secondary alcohol. So that the SN2 chemistry, we know by the rate, things that are primary react faster than secondary. So how are we going to deal with the primary alcohol in the presence of the secondary? So we have to consider that before we even get to substituting at the secondary center. So with everything we've learned so far, these are the challenges that we have to address. There's increased reactivity at the primary alcohol over the secondary. So how do we block? So I'll underline that. How do we block the primary so that we only work at the secondary alcohol? We know that OH is a bad leaving group, so we need to do something about that. And then we need to address the inversion issue. So there's 5 reactions we'll carry out, and we'll show those on the next slide about how thymidine goes to AZT. The first issue we're going to tackle is dealing with that primary alcohol. We know that overall it's left untouched in the product, and we have to get rid of its reactivity relative to the secondary alcohol. So the first thing we do is we protect it. So basically the H is then substituted for this group, which is called a protecting group. So overall, what it makes is a silicon oxygen carbon bond, and that's called a silicon ether. And so the substrate we use is shown here, which is called TBS chloride. So oxygen likes to form bonds to silicon. If you go to the beach and walk through the sand, it's a lot of oxygen silicon bonds in sand. So those are pretty stable. So you'll notice that the reaction, there's an H in a Cl. That's the chlorine's the leaving group on silicon. And so this compound here, imidazole, is a base that neutralizes the HCl formed. So now we've dealt with that issue of the 2 alcohols. The primary alcohol is no longer in play. The next issue at the secondary alcohol, we know that OH is a bad leaving group. So we have to transform it into a good leaving group by removing or substituting the H. So this H then gets substituted for that. And now the whole thing is a good leaving group. So those were the sulfonate esters that we learned about. And so what is interesting about the reaction sequence is the molecule has a nucleophile within itself that will displace that leaving group. And so that specific hydrogen that I've highlighted, that's pretty acidic because it's sandwiched between an amide and a urea. And so that can be deprotonated with sodium hydride. So that's a base that will act as an acid. initially it'll put the lone pair on the nitrogen, but through resonance, it can be delocalized onto the carbonyl oxygen, which will act as a nucleophile, like within the molecule. And that's called intramolecular. So I always think back to Rhodes when I try to differentiate intramolecular and intermolecular. So the interstate runs between like Mississippi and Florida. So that's two different things. That's inter. Intra means within. So a nucleophile and electrophile within one molecule. And so I drew that really long, weird bond here. That's showing you that the oxygen attacks that carbon to displace the leaving group. So you've done one of the inversions, and then in the next step we'll treat with the azide, which then attacks that carbon to retain the stereochemistry. So notice this word changed here. So now the nucleophile and electrophile are two different molecules. So Na plus, N3 minus, that attacks that 180 to the leaving group. That bond breaks or sort of leaves, but the leaving group is retained in the molecule. And so now you have retention. So we have the azide in there where it needs to be in the right stereochemistry. The last issue that we have to deal with is now removing that group, and that's called deprotection. So we need to get it back to the alcohol. And this happens through an SN2 reaction. So this reagent here is N plus. So it has 4 butyl chains on it. And then the counter ion is F minus. So the F minus is a nucleophile. It attacks the silicon. A silicon-fluorine bond is much stronger than a silicon-oxygen bond. And then it breaks that bond. And then the hydrogen comes from the workup, so an aqueous workup. So that's one way in which AZT can be made. There are probably others that are more efficient or give higher yields, things like that. So that was a 5-step sequence to produce that molecule. And so remember, for AZT to end up in a pill at the pharmacy, it has to be made synthetically. And if there's hundreds of pill bottles at that pharmacy, you can imagine the route to get that pill into the bottle takes quite a bit of time and effort from these companies that make them. Any questions so far? Again, I think what you'll see as we move forward in these sequences, there's the individual reactions, but then you have to put them in the right order, but they're all relying on the mechanisms that you've learned. You have a question?
What do you mean the hydrogen comes from the water column?
So from this, after the fluorine attacks, the ball is the rest of the molecule. That's what you get. So that needs to be protonated. And so a lot of reactions have an aqueous workup. So you're dumping in water of some sort, whether it's acidic or basic. And so at that point, if you're doing an acidic workup with hydronium ion, this would be a proton transfer. So again, that relates back to Module 3 when we talked about acids and bases. So I do want to introduce SN1 today because it relates to this rate trend for SN2, where we talked about tertiary substrates don't react by SN2, but they will do substitutions by SN1. And the reason they can do that is because now we're changing the solvent and the type of nucleophile that we use. So I can't stress this enough. It's important that however way you classify things, however you learn flashcards or mind maps or whatever, that when you look at these classes of reagents, you sort of know their reactivity. So that the SN1 mechanism, the 1 stands for unimolecular. So the concentration of the electrophile now is the rate limiting step. So the carbon bearing the leaving group, that's the concentration that matters on how fast the reaction proceeds. So 1 is unimolecular. And a term that's associated with that is solvolysis. So you've heard of hydrolysis. So lysis means cleavage. Hydrolysis is just cleavage by water. Solvolysis is cleavage by whatever solvent is in there. And to preface how different this mechanism is now, the reaction coordinates are a lot more complicated. But within there are the terms we've already seen. So on this reaction coordinate, it's asking you to identify from the Roman numerals what positions are transition states. So notice the term now is plural, transition states. It's not just one. So as the mechanisms get a little bit more complex, they can go through multiple transition states, but only one of them is going to be rate limiting. So that the highest points are the transition states, so that's C. And now it says intermediates. So the starting material is position 1, the product is position 5, 2 and 4 are transition states, and so intermediates are the wells. So this is a well or a trough, so that would be B. And the reason there's a difference between a transition state and an intermediate is the lifetime. And when I say lifetime, I don't mean like human lifetime. So we're talking in like micro or nanosecond lifetimes. And so if we draw a line down from sort of each side of that well, this is what I mean by lifetime. Because overall, that x-axis is time. Because it spans a little bit of distance, whereas a transition state really is just a point. It has, that distance is much smaller than an intermediate. So, again, if you're pushing that ball up the hill, it can only exist at the top of that hill a very short time. But then when it goes into the well, it can sort of move back and forth in the well a little bit longer. And as a consequence of that, it allows it to go different paths. So even though this is a slice, if you imagine like a mountain hill, it could go down that way or that way, depending on the way it's coming off that transition state. So a complicating factor of this coordinate is you have two transition states, and remember, those are always higher in energy. So which one of them is going to limit the rate? And the way you figure that out from your starting material position, just draw a dotted line or a dashed line all the way across, and then look at which hill is higher to climb. So between transition states 2 and 4, 2 is the highest. So that's going to limit the rate of the reaction. So this would be A. So notice the rate trend now for SN1 is inverse. It's the opposite trend. Tertiary reacts greater than secondary, which is much, much greater than primary. And the secondaries are really the one that require more diagnosis. Because they overlap in both mechanisms. And that's when you have to look at the nature of the nucleophile, the nature of the solvent to determine is it SN2 or SN1. So the reaction that we'll look at for SN1 is this molecule called tert-butyl bromide. And so it's a tertiary alkyl halide. And so ethanol is the solvent. And then notice the substitution that has occurred is bromine for O-ethyl. And so now we end up with an ether. So one thing that should stand out to you is when you look at that reaction, you do not see a nucleophile of the form metal plus nucleophile minus. The only thing you see is solvent. So for a lot of SN1 reactions, the solvent is the nucleophile. So the nucleophiles in this mechanism are neutral, and we call them weak. So how does this occur? So the other thing to notice, the solvent is now protic. There's OH, and that really facilitates starting the mechanism because the carbon-bromine bond, we know that it's polar covalent. The protic nature of the solvent essentially is it's going to be attracted to that delta minus, and it's going to start tugging on the carbon-bromine sigma bond. So I'm going to draw that with that dashed line to indicate like a hydrogen bond. So we know that's delta plus, that's delta minus. So there's that electrostatic attraction that is essentially helping to elongate the CBr bond. And eventually that bond gets long enough that it breaks. And then since this is an ionic reaction, the bond ionizes. So you form a plus charge on carbon and a minus charge on bromine. So that's what we mean by ionization. And so now you have this carbon that's plus. So that's electrophilic. The ethanol has lone pairs on oxygen. Those are nucleophilic, and then that will attack. So that's the substitution. So let me use the last minute to run through this slide, and then next week we're going to talk about the reaction coordinate of this, and you'll see it looks a lot more complicated because there's more things that are happening. So the slow step in SN1 is the ionization, because you're going from something that's neutral and then you're forming two ions. So because it's a carbon with a plus charge, it's called a carbocation. And then you have the bromine, Br minus, bromide ion. That's higher in energy. This is called an intermediate. So that's not a transition state. It lives a little bit longer. When the ionization happens, the carbon changes hybridization. So now you have a p orbital. The nucleophile can attack either lobe of that p orbital. You end up with this other charged species called an oxonium ion. And then that undergoes acid-base to get you your neutral product, so your ether. So we're about out of time, but I'll explain that again on Monday, and then we'll look at the coordinate to see the difference between transition states and intermediates along this mechanism.